Well, I'd like to welcome you to the update lecture.
He's a PhD astronomer, and I took his desk over at Michigan. He graduated. On the 10th floor. Neither one of them wanted it.
My name's Gary Tomlinson, and for the past 10 years, I understand, I've had the honor and privilege to introduce our update lecturer. The purpose of this lecture is to present the latest astronomical information, correcting all the information from last year that was true last year. For those who don't know me, my introductions have been anything but traditional. Ron and I have been friends for over 40 years now. We're both still hobbling around, but we're still here. But last year, a significant event happened. GLPA instituted the GLPA Code of Conduct. It's the first thing in your conference notebook. 2 times, the GLPA president has reminded me we have instituted the Code of Conduct. And I thought I'd better read it to you. It says, right here, it says, we pledge to treat all people with respect and provide a harassment and bullying-free environment. So I looked up the definition of all. I'm tied. So then I looked up the definition of people. So I guess Ron marginally qualifies. And especially after this morning, it doesn't leave me many options other than to say, ladies and gentlemen, Dr. Ronald H. Kachuk.
I don't need these. Trust me. Oh. As I was preparing this talk, I seriously, at one point, getting, kind of frazzled and behind schedule and all that kind of stuff. Did anyone here know if I used the one from 3 years ago? Maybe the best of. As always, there was much too much to talk about. I wanted to cover all of it. Unless you wanted to be here for 3 to 4 hours. I'm not joking, because I threw out 80% of what I had clipped. And then I still had to compress, and in fact, I'm going to have to start going here pretty quickly. Still got too much to do. And I'm selective. I take things that, A, have to interest me, very frankly, if I'm going to talk about it, but B, something I think that interests you and be useful to you, and particularly from the standpoint of dealing with the general public. The general public hears and sees things that gets them interested or excited, and it's not necessarily the thing that has any effect on a professional astronomer. I have to kind of be careful. Let me start. Let me get going. I don't have time. I want to talk about a couple of people before I get too far into this. Jocelyn Bell Burnell finally got some recognition. In 1967, part of her dissertation at Cambridge, University, England, discovered pulsars, the first pulsar, and had at least a little bit of trouble, so I'm told, with the grapevine, convincing her dissertation advisor, Anthony Hewish, that she actually found something significant. He said, no, what you're picking up, by the way, what she picked up was a click, 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 about once a second. And the radio telescope she had built for the study she was doing. The radio telescope, by the way, consisted of a 1 acre or so area that was covered with chicken wire. Honest to God, that was the intent. It was the right one for what she was trying to do. But anyway, as you know, of course, we indeed had pulsars. The Nobel Prize went to her dissertation advisor. back then, you don't give Nobel Prizes to a woman or a grad student. She was always very gracious about it, exceptionally so. Even though she had lots of people who told her she had a right to complain. What she won, though, just recently, was a $1 million award, actually a $3 million award, from the Breakthrough Foundation. And in keeping with her character, she's giving it away. It helps students, especially underrepresented groups of students, succeed in science. That's cool. It really is. I don't know that I could be that gracious if that happened to me. I'd be complaining here. Of course, we all know Stephen Hawking. And I could talk for, any of us could talk for a long time about this. He passed away at age 76. He changed the way we look at black holes and think about black holes in marvelous ways. He had an incredible mind and an incredible disadvantage. See, he was a role model in many ways. Okay, let me go to a list. Number one's already sitting down, so we're through that. I was tempted to add you, but anyway. What I'm about to put up on Bulldog, this is legit. This is not a joke. It's going to look like it. A planet with two south magnetic poles, only one north pole. All you've ever taught electromagnetism, think about that for a minute. Wandering planets without a host star, just floating around. A star that won't die, clarify that. And this is the one you want to stay awake for at the very end. Galaxies without stars. You thought you knew the definition of a galaxy, didn't you? Hang on. Well, let's start close to home, the solar system. No? Okay, sorry. You want to sign up for the Neighborhood Watch? In a sense, we do. For the incoming asteroids and stuff. And in particular, as you know, we had this guy, which is interstellar. Amua. By the way, if you're Hawaiian, I apologize for the pronunciation. Otherwise, I said it perfectly. You heard all kinds of things about this one, that it was elongated. It was 8 times wider than it was width. I want you to know where that came from. There's no pictures of this. That's an artist's conception. It's from the light variation. This thing apparently is tumbling with about, I think it's an 8-hour period. And the light goes up about a factor of 8. So we're getting a width to that. We're figuring when it goes elongated ways towards us, we don't see as much area. We get less light, sunlight reflected to us than when it goes broadside. That's how they came up with that dimensions. By the way, there's other ways to do that. And any of us could think about that for a while, come up other way. True. They first thought this thing was an asteroid, having every year I do this talk, I start coming down cold. I want to have to drink water all the time. I thought this was an asteroid because we didn't see it venting any dust or gas like a comet ought to do. That got out to the media. Oh, it's an asteroid. Sometime later, we all heard, no, it's a comet. It's a comet because its orbit was being altered very slightly, as comets will do when they're venting gases and they get close to the sun and they get their ices sublimate and they have to break through the crust and they form little jets. And this thing seemed to be doing that. Okay, fine. Then we heard, this is the last round as far as I know, no, it's probably an asteroid. Because if it was venting these little gas jets on its surface, like Halley's comets and others, enough to change the orbit, it would have also changed the spin. It would be speeding up. There's no way those jets would be exactly on the center of mass. to be off some distance, give it a lever arm and spin this sucker around. How do we know it's interstellar? Well, you can figure out its orbit. The first indication was its speed. It came in with an enormous speed, clearly not bound to the sun. It was going to wrap around the sun and head back out. No way it was going to stop. Where did it come from? That's hard to know. You can track back in time, the trajectory back in time, but remember, the stars aren't fixed. And this thing has been traveling for who knows how long? Millions of years? Tens of millions of years? And so those stars have all moved. There is a candidate right now, which is the best candidate, which is a red dwarf star, HIP 3757. The only problem with that is the closest approach it ever made to the trajectory of this asteroid, comet, whatever it is, was about 2 light years. I don't know about you, but 2 light years isn't close. Okay. We currently have rovers running around in this asteroid, and I don't know how you pronounce that, Yuga or something. I swear they pick these targets, that's throwing me off. The Japanese have done this, Hayabusa 2, and this is a close-up picture from one of them. They have 2 rovers, small rovers about the size of a microwave oven. They're on the asteroid, and to rove on a small irregular object that has almost no gravitation to speak of, what do? Well, wheels don't work too well. So what they did instead is they have an arm inside this thing, which has a weight on it. They swing around and causes the thing to hop. So it's jumping. They have 2 of them. There was a third one that was on battery power. Those first 2 are called Minervas. They work with solar panels. This other one's battery powered because it has different instruments and so on and so forth. And it lasted 17 hours. It's and Hayabusa 2 is going to do the following. It's going to return eventually 3 samples from the surface. Hayabusa 1 tried this and came back with some dust. They're hoping to get more this time. It literally changes orbit, drops down so close that it extends a funnel down to the surface and attracts some material. So it's got three attempts to do that. The third attempt is going to fire a ballistic missile into the missile being a copper weight into the asteroid, dig a hole into the crater, then go down and sample that. That's fresher material and deeper. And then all this is coming back to Earth December 2020. I'll have to keep an eye on that one. You know, when I was a kid, God, it wasn't that long ago, Jupiter had 12 moons. I remember I was being proud of myself. I knew that fact. And I always could startle and amaze as an adult. 12 moons. That's 12 moons. Forever, 12 moons. We're up to 79 now. And the question we all have at some point is how small these suckers have to get before we stop calling them a moon. I don't know. That's even a stickier problem than how you define a planet. Thinking about it. The new ones, the 10 new ones, were discovered with the 6.5 meter Magellan Ada reflector at Las Campanas Observatory, South America, and the 40 meter Blanco reflector at Cerro Tololo. These things all orbit in families. I've got some color-coded families. So the newest ones actually go around the opposite direction. They are probably fragments from collisions. So as bigger objects hit and broke apart, they continue up more or less off in the same direction. All right. Stand by for weird magnetic field time. This is a picture of Jupiter. Magnetic field. As every textbook will tell you, it's bipolar magnetic field. Hogwash. I wish. From the distance we've been mapping it and seeing it, that's the way it looks. We now have the Joe space probe that's swinging in really tight and flying over the equator polar orbit. We're getting magnetometer measurements we've never had before. This has now been mapped, and it's startling. Let me remind you about magnetic fields. Oh, by the way, you can see those white bright areas. Oh, let me get my laser pointer. That's supposed to be able to do this. Oh, how about that? We've got these areas here and here. This brighter is actually a donut that goes around. It's trapped radiation. That's the reason all the spacecraft, including Galileo, that was orbiting this for years, stayed outside of that because they fried their electronics trying to cross through that. Whereas Jove, you might remember from last year, I talked about, it comes over out through here, it goes through the whole of the donut. It gets very close to Jupiter. Now, we talk about magnetic fields. This is the stuff we teach in physical science. We've got a little battery here, and we connect the wires, and this is a curl of wire, and you sure enough get a dipole, or you get a bar magnet, you get the same kind of thing. Down on the Earth, we think we've got charged particles that are being moved around by the spinning Earth, and of course, convection as well. And this combination creates a magnetic field. All right. Now let's see what Jupiter looks like up close. Yuck, actually. The North Pole, this entire area up here, and then the fuel lines come on down. They go two places, to a broad area in the south and to another spot near the equator. No, I don't know what's going on. We don't know. Oh, with the rotation. Yeah, it must. Anyway, fields aren't simple. In this case, of course, they're being created by electrical currents, which is actually gases. Remember, we got this metallic hydrogen stuff going on. And also, this is not coming from the core. We've already determined that. This is very shallow where it's being produced. So all our ideas about magnetic planets have got really kicked in the behind over all this. We have a lake on Mars. And by lake, I mean a lake of liquid water. The Mars Express space probe, which orbits Mars, has an instrument on it called the MARIS, the Advanced Radar for Subsurface Ionosphere Sounding. It's just two booms, and they've got transmitters on them, and they beam radar down to the surface as they orbit, get the return echo. Because of the wavelength, this stuff can penetrate the surface, in some cases up to 5 kilometers, believe it or not. And that by the return echo, they can see things. What you see over here are some of these stripy things. Those are different passes over this spot, which is near the South Pole. There's the ice pack down there. And what you see here is there's one spot where you get strong reflection, color-coded blue. You also get some spectral information from that of what might it be. Liquid water. That's quite a trick because it's probably about 60 below zero there. Well, you can get away with it with salty water. There's more another cross section. Mine is by the depth of that's 1,500 meters. So, if you can make the water really, really, really salty, it can stay liquid. Mix something in with salts, obviously. Well, Mars got all kinds of salts. It's not a problem. Now, on the surfaces, we're seeing water. Water ice. This is the clearest evidence yet. Now, this image you're seeing, the blue, is color-coded enhanced to mark the location. This is from orbiters. There are sites, several sites. They're not near the pole, really. They're like latitude 50-ish. We're seeing these, both north and south hemispheres. And this is being exposed. We think with time, the ice is sublimate, the rock embedded in it falls away, and this kind of eats away into the interior. This is not something that comes and goes with seasons. This is there all the time. And of course, we've got one working rover, and it's, as you've probably heard, discovered organic compounds on Mars. Organic compounds involve carbon, obviously. What gets people excited is they go hand in hand with life. Not that it tells you there's life, but if we never found the organic compounds, it would probably tell us there wasn't any, or even in the past. This particular area was an ancient lake. It looks like it has all the conditions that once upon a time would have supported life. course, opportunity, that one's curiosity. Opportunity, not doing well. It may be dead. The dust storm completely covered over the solar panels. Solar panels weren't actually to make it run. They were to make it charge the batteries. Batteries were critical to keep the heaters on during Martian night. Because if the thing gets too cold, then it warms up somewhat in the daytime, well, circuit cards, all comes back to electronics, crack. That was the critical thing, was to make sure these things never got too cold. Hard to believe it hasn't happened, but it's not responding. It could be because it's not charged enough yet, because there's so much dust covering this thing, or it's just dead. Time will tell. When we talk about water, for years, I thought I was doing the right thing, that the moon was stone cold dry. Absolutely. I got that from the lunar samples brought back by the Apollo astronauts. And all that was done, well, that conclusion they drew on those samples was an error. Now, no. You know, scientists, by the way, are humans. They make all the same mistakes all humans make. They came in with a preconceived idea, and people were analyzing it, and when they got signs that there might be some trapped moisture, they said, obviously it was contaminated. That's what happened. They would have known decades ago about the water on Mars, if they had, on Moon rather, if they had just not jumped to the wrong conclusion too soon. And you see the image there, we got the polar regions, the South Pole and the North Pole, South Pole on the left. And the areas that are speckled kind of bluish. That's where water ice has been detected from orbit. And I mean it's on the surface, or matter a few centimeters down, help yourself. It's in craters that are always, the bottoms of craters, but they don't get any sunlight. So they're always cold, super cold. If you put ice out on the moon, any place else where sun is, it will sublimate. There's a considerable amount of ice. I'm now willing to bet, at least many people are, that if you want to know where you're going to find life in the solar system other than Earth, maybe here in Enceladus. Putting higher marks on this than we do Mars right now. I'm not talking about life once upon a time, I'm talking about life now. It's an amazing place. It, well, which I think you all know, it tends to have these geysers. Galileo probe actually flew through that, analyzed it. Water. Well, water ice, actually, because it freezes as it comes out of those geysers at the surface. But it's not new. What is new is further analysis of all that information turns out that some of the stuff that picked up in the water were organic molecules that were extremely complex, like atomic mass units 200. Much more complex than methane, for instance. That's the kind of thing life does. So, is there an ocean down there? Are there geothermal vents which provide the warmth, the energy for the life? And the vents come from the fact that we got the tidal effects of this big planet, pulling on it, stretching and squeezing. Now, we've got geothermal vents in the Earth, oceans as well. We have examples already. I'll read you a quote from one of the researchers. I should have put this on the screen. Complex organic molecules emanating from its liquid water and ocean, this moon is the only body besides the Earth known to simultaneously satisfy all the basic requirements for life as we know it. That's a really powerful statement to think about. Onto Enceladus. Oh, you remember the hexagon at the North Pole of Saturn? Okay. Here's the funny thing. It's only at one pole, the North Pole. And what's happened over the last few months, I don't have a way to point this out, I don't have a good illustration, but because of seasonal changes, There's now sunlight hitting some of the atmosphere above the planet at higher levels. And they've been watching the motions of this with Doppler imaging and things. Guess what? The hexagon pattern goes all the way up for at least 200 miles. And no, we don't know why it's doing that. We have something going on in the troposphere which is affecting the stratosphere. That's supposed to happen. Well, it's not the Earth. Okay. Let's see if this is going to work on your screen. I hope so. Oh, yeah, there we go. Two pictures. We're blinking back and forth. This is just a few hours apart. And we've got a moving object. That's how you can pick them out. If something moves like that, it's part of the solar system. This is called 215. In other words, the year it was discovered. TG387. Oh, I'm not going to remember that. So we have a nickname for it. This is called the Goblin. Yeah, you will remember. What's important about this thing is its orbit. It goes way out. It goes to the inner edge of the Oort cloud. I don't know if you can see this or not, but the little hazy area in here, that's the Kuiper belt. I mean, this is amazing. Sedna, we used to think that was far out. And so what's the other one I got up there? Oh, that's just has that number more recently, 2012 VP, whatever it is. But notice all these orbits are on the left side of the screen. There's about a half dozen more that'll do the same thing too. And this is what's led to the discussion, search actually, for Planet 9. Because those orbits just don't do that randomly over time. They will just randomize. The orbits precess. They don't stay all pointed in one side. That just doesn't happen. Unless there's something gravitationally that's encouraging it, shall we say. And so the thought is Planet 9 is off to the right here, way off your screen, and it has a mass that's significant, many times the mass of the Earth. It may be 700 AU from the Sun. By the way, this guy goes out 2,300 AU, if I'm not mistaken. It's way out. We've captured it right now while it was in close. It was out at its far point. We'd never see it at all. Exoplanets. Nothing happened there, right? It's interesting that I'm at a stage now, new discovery. Oh, it's just another planet. Yeah, that's not even that important. It is. I can just swat at another mosquito. It doesn't seem to mean a lot. The fact that that happens so fast is amazing. There is a contention based on models that super-Earths, which you have to be careful with that definition because people define it in different ways and don't warn you, planets that are larger than the Earth but not as big as, say, Neptune. Neptune's fine. Large part of them have tremendous amounts of water. Tremendous amounts. This is based on models, looking at the sizes and density. Oh, one other thing I'll warn you about. When you talk about this kind of stuff, you'll see in the media or literature, talk about planet sizes. Now, most of the time when astronomers say size or gets quoted about size, we're talking about mass. This is the one time where we're not. We're talking about size, width, really are. That's what we're looking at, because we get the size directly from transits. So that's what we've been using. Anyway, get what I was saying, that there are models of this thing, try to mimic size and measure density. What's the composition? Some of these by weight are going to be 50% water. The Earth by weight is 0.02%. In fact, there could be some of these things which are nothing but water. Oh, and by the way, a number of those are in habitable zones, by the way. Then we have planets that aren't doing what they're supposed to at all. Artist's conception, in case you didn't get this is not a real picture. no idea what the sucker looks like. It's been detected, and it does have a name. Stand by. SIMP, SIMP, J 013656663 plus 0933473. I'm sure you all will remember this going on. It's been detected with radio telescopes because it has very strong radio emission from aurora. This thing has got, for some reason, a very strong magnetic field and very strong aurora outbursts. Now, what makes auroras on Earth? Solar wind, and this doesn't have a star. It's there in interstellar space all by its lonesome. However, what we've learned from the Jove probe over Jupiter is Jupiter doesn't need the sun either. However it's happening, the particles, the charged particles that make up the aurora of Jupiter are being pulled out of Jupiter itself. They're not coming in from the sun, they're coming out of the polar regions. So this could be doing the same thing. It's a big planet, by the way. It's 12.7 times the mass of Jupiter and 1.2 times the radius. It's right on the border of being called a great dwarf, round dwarf. Rogue planets are not that far, not that, there's 17 known. It's not the first one. In fact, here's a binary pair. Now, how many binary planets have you seen? I mean, two planets the same size, as far as we can tell. Certainly don't have that in the solar system. You get all kinds of questions about how could that be. I give its name, but it's even longer than the one I just read to you. In fact, it's almost twice as long, so I'm not going to try.
What do you mean by rogue in this context?
Well, it's what's been used in the literature a lot, the popular literature at least. It means it's just not attached to a star. It's just free tweedling around or whatever. This particular one is actually part of a group of stars, we think. TW Hydrate Association. I forget how many stars are in that group. These are groups of stars that are not necessarily all that well bound together, but they share a common motion, a common direction, traveling the same way. This is in that group. It's about 160 light years away. Binary separation is about 4 astronomical units. Each component is about, since they're orbiting, you get the mass, about 3.7 Jupiters. And there's this guy, ELT 9b. It has iron and titanium in its atmosphere. The only way you do that, you do it by being really, really hot, 4,000 centigrade. Probably one of the cooler pictures of the year is this one. This little bright spot there is a forming planet. This is the disk around the star from which it's forming. It's cleared out a hole in this area. In fact, to make it glow requires energy. The energy is coming from accretion, matter falling in. And from the energy of the light, we got an idea of the rate. Does it make sense? It does indeed. It's coming in at about 10 millionths of a Jupiter's mass per year. It's growing. Never seen this before. More cool things are going to happen with exoplanets because TESS is operational. And I don't have too much to say about it, except this is the successor to Kepler. The big difference is this one can point all over the sky. Kepler was locked into one area at a time. Had been the area from Cygnus, as you know, for 6 years or so. Then it went to the K2 mission where it went along the ecliptic. Now it's, as you may know, is in safe mode basically because it's run out at the end of its life. Try to conserve the fuel they use for pointing. TESS doesn't have those restrictions. They can point anywhere in the sky. The difference will be it's going to go for brighter, closer stars. Kepler went really quite faint. This one don't. And so we're going to have, and it can, target places, but it's going to map the whole sky. The whole sky. And it's already found 2 exoplanets, by the way. Did we find, or did somebody find an exoplanet? First one. The Media's already decided it's true. I want to show you what this is based on. And I want to make sure you understand I'm not putting this down, or the researchers. This is very hard to do. But even they would admit it's not a sure thing. What they did is they looked through the databases for Kepler. By the way, any of you can too. Kepler's data is all available. And they were looking through the data, looking at transits, one in particular, and did they see any sign of that transiting object having a companion also blocking some light? Less so. It would be smaller, like you see in this artist's conception. Here we go. Oops. There we go. Okay, these are all transits. Let's look at the bottom three here. This illustration in the original paper had to do with how they were processing the data and taking out trends and stuff. And the only thing I really want you to look at is this one. Here's the transit. And then when the light goes down, this is brightness versus time. The light goes down because the planet is coming across. So it drops us down about 1% or so in brightness. And then it travels all the way across the star and then comes out again. But then it looks like it goes down again. Notice this little dips here and here as well. Now, that's what it's all based on. Remember, the vertical bars are the uncertainty, the error bar. So when you have an error bar, it means the measurement really could be at the top end of that bar or the bottom of the bar. It looks like overall, on average, these are a little bit lower, but boy, you better figure out this level perfectly before you conclude that. The trouble is, what they're trying to do, even with Kepler, it's a really hard thing to do because moons are small. This time the moon is estimated to be the size of Neptune. Big for a moon. I'll show you another example. This is time again versus brightness. So let me come back to the end of the transit. Here's where the light comes back up as the planet finishes going across from the star, and the level comes up to here. While it was transiting, the level was down here. Now, the other half over here should be a mirror image. It's not a mirror image. It's almost too depressed in this area compared to over there, and the bottom is a little bit dimmer. Well, it turns out you could get that amount of dimming if you had a moon about the size of... Oh, one big difference. State is mine. This is one I'm looking at. And while I was talking to a class about it, I looked at the screen and I said, it's weird. I've seen other transits on this system, and that's not a normal feature. So, I run to the media and say I have a moon. Am I sure? Maybe. What would you have to do? This is one of these learning things. I turn this into a thing for my class. Okay, gang, maybe I found an answer. What do I do next? Okay. What do I do next to convince people? Or not? Determine when I get it wrong. Oh, we've got to look more. Yeah, a lot more. A lot more. For one thing, the moon's going around with a different orbital period, as its own orbital period, compared to the one for the planet it orbits. So you really got to almost hit or miss whether you're going to pick it up. A little bit about stars. You know Albireo? Well, not a binary. All these years, we were hoping it was binary. You get people in the observatory or whatever, in the eyepiece, look at Albireo, and they can see these pretty colors. You can see color with your eyes in your eyepiece. You don't have too many objects. You can do that. These are very clearly, kind of a gold color of a blue star. It turns out it's completely accidental alignment. How do we know this? A space probe called Gaia, Europeans. It's a huge mapping. That's a whole topic in its own right. I don't have time for it. It's measuring something like over 1 billion stars and is getting motions. If those two are binary, they have to share the same motion through space. They're a unit. Guess what? They're going different ways. Just happen to be, our perspective aligned right now. Last year, I told you about a pair of stars that are going to explode. In 2022. Yep. What was happening was these two stars, which are already in contact binary, were getting closer and closer together. By the way, contact binary is not the least bit controversial. These are well established. But these things we're losing angular momentum, producing gravitational radiation, we would presume. And they're spinning together, and the rate, and they can see that because the period was getting quicker, quicker, quicker. As they're getting closer, 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 like a egg beater speeding up. And so all you had to do is, time the orbital period it was picking up. And so you could make a prediction when they would, come together and go boom. So we all got excited about this. I mean, a lot of projects, a lot of observing got started, a lot of students got into this. The trouble is, a grad student looked at this again from San Diego State and discovered there was a screw up in the paper. Not their paper, but the paper that those original researchers quoted. See, what you need are time schedules where people have seen eclipses of these eclipsing binary, so you can time things out. There was a typo, of all things. There was a preprint draft, then there was the published paper, and they didn't have the same numbers. This happens. You correct the typo, it's doing just fine, thank you. It's going to go around forever. There was Tabby's star, you probably remember this one. This is one that had alien megastructures around it and all that kind of stuff. Okay. But in fact, we didn't know what was going on. We have a little bit better idea now. I need to remind you what happens. This is a fairly bright star. It's normally just very constant brightness. And then those episodes where it just dims. And sometimes goes, and it's not a transit of a planet or even another star, but it just dims. And sometimes 20%, sometimes less. It's erratic. Nothing periodic about it. Well, we now know that when it dims more in blue light than red light. That's dust, not an alien megastructure. A solid object, like a megastructure, it's not going to be wavelength dependent. This is very wavelength dependent, very much like interstellar dust. So this has got some kind of dust disk around it or something, inhomogeneities or density or spots to come across and cause the light to drop. Here's a star that wouldn't die. This is a real mystery. See the panel on the left? Supernova, distant galaxies, 1954. One on the right just shows years later, yep, sure, it's gone, just like it's supposed to happen. Supernova goes off, blows the star to smithereens, end of story. Except, 2014, it did it all again. In fact, multiple times in 2014. I want to point out to you the units here. These are brightness in units of billions of suns. Not millions, billions of suns. And so here, this little peak here is an increase of over 1 billion solar luminosity. So you got this whole event, but you got all these minor ups and downs, each one a mini supernova, and it just keeps going. And explanation? Duh. Can't do that. It's something very different than our supernova models, that's for sure. I'm about to show you several funny things about supernova. I hope you don't think we have them all figured out. Not even close. Now there's the supernova. This particular one is in a galaxy about 200 million light years away. Based on that, and the apparent brightness of that nova going off, we can go ahead and estimate its brightness. It's rather 10 to 100 times supernova. These two pictures are just showing a way of subtracting out the light of the galaxy, so what's left is just the supernova. Spectra doesn't make any sense. The pattern of brightness changes doesn't make any sense. And then there's these things. There's something or others. We now have seen 72 of these. They're bright like supernovae. They're in galaxies. In fact, 72 have recently been discovered in archive class. The difference is they get bright and dim really fast. So they've been called fast evolving luminous transients, or FELTs. Why not? Let's come up with another one of these things to remember, right? FELTs. These things change on time scale of days, where a supernova does things on weeks. Again, we don't have models for this. And we saw a black hole eat a star. Yeah, really. I've explained the diagram here, which is, of course, a mess. Here's an actual picture from Hubble of colliding galaxies. We've got a little area here that enlarge, and then we have an artist go nuts and draw this for us. Idea of this star here is getting pulled away, teared apart, torn apart, spinning around, making the accretion disk in a jet. All right, everything in the box is questionable. We don't know. Watch the animation I'm about to run. This is actual data. Time's going by. Right away, notice how it starts to elongate. When it gets to the end there, it elongates. I think those are the jets being produced by the heating of the star. This is in a massive black hole in a galaxy, I forgot to tell you. There's the outburst. All this, like all science, requires interpretation. That's the current interpretation. History's been made this year. We now have something called multi-messenger astronomy, or multi-messenger science, because multi-messenger is the key here. And this comes about, number one, the first example here is gravitational waves. As an astronomer, I have a project to do. Well, I've got optical telescopes at my disposal. I can put in and ask for time in radio telescopes. I can sometimes ask for time or at least data from X-ray telescopes or gamma ray telescopes. In other words, but everything I'm asking for is part of the electromagnetic spectrum. And that's all we've ever dealt with. Now we're being handed something that's other than that. And it's going to take us a long time to wrap our brains around using it effectively. And gravitational waves is what I'm talking about. Well, LIGO detected its fifth gravitational wave event. The fifth one was different than the others. The others were events that lasted ripples in space-time, which lasted a fraction of a second. This one lasted 90 seconds. Weaker, went on for 90 seconds. It matched exactly what you'd expect for the ripples in space-time if you had two neutron stars that were spinning around each other, losing energy, gravitational waves, causing the energy to come from the orbital motion, so they start falling together, and the speed goes up and up and up and up until they finally merge, fall in and merge. Spinning white, orbiting white dwarfs losing gravitational energy has already been confirmed in pulsars. We already know all about that. So that's not a strange idea. But seeing it die is something else. Well, you'd like confirmation. The LIGO team, using both their detectors and the one in Italy, was able to get an area sky roughly where this thing came from. And they had already secured alliances with optical astronomers around the world, about 70 people. They had to sign a very extensive non-disclosure agreement to be part of the team. You're not allowed to brag or anything on what you find until you come to headquarters, as it were. So these people got the alert, got the location, looked for something. Maybe it's still there. It's still glowing. Maybe it's some event. They did give the optical astronomers a distance, 150 million light years. Oh, it's a galaxy. In the area sky, they indicated there weren't that many galaxies. And there weren't that many at 150 million light years. This one is, it had an outburst. dot there, which is highlighted by shading it dark, I don't know why they did that, wasn't there in the earlier pictures. This site has been surveyed. And that little dot is possible to get spectrum. Spectrum of the galaxy gives distance from redshift. It's 150 million light years. That little dot is 1,000 times as bright as a normal nova. So, oh, and there was a gamma ray burst at the same time, the same location. Gamma ray burst has been a mystery for decades, what they really were. Oh, once a day there's just a gamma ray burst somewhere in the sky. Now, no. Neutron stars. Why? It's confirmed. These kind of mergers produce a lot of heavy metals. I'm talking about the nuclear processes that happen at these high temperatures. In fact, it's kind of important because you all know that all the heavy elements, all the elements come from stars. And we often just say from supernova. There's a little bit of baggage maybe you didn't know about. It's not perfect. The highest atomic weight molecules, atoms, in fact, aren't properly accounted for by supernova. They are if you have neutron stars. So this little event confirms that the majority of the heavy elements with masses higher than iron were produced by neutron star collisions. In fact, this event produced enough gold, it's pure gold, 10 times the mass of the moon. This is how I get Congress interested. You must fund astronomy. One last thought on all this. These two stars, we now know their masses from the gravitational wave data. They were about 1.5 early. 1.48 and 1.26 solar masses. You add that together, allow for a little bit of mass loss, you get a final object. Once it merged, it'd be about 2.7 solar masses. And the question is, what is that? It's too massive to be a neutron star by understanding of neutron star limits. Yet, that'd be the least massive black hole. So what did it make? Black hole? Or a weird neutron star or something else? Multi-messenger astronomy. What was used was things from the electromagnetic spectrum, visible light, gamma rays, and of course, gravitational waves. Example 2, very quickly. This is a thing called the ice cube detector. It's in the South Pole. And in fact, Michigan State's involved in this, if I remember right. There are underground detectors. Most of the detectors are in the ice underneath it. And the idea is they can detect neutrinos, these really subatomic particles which don't usually interact with anything and go through light years of lead and all that kind of stuff on average. They're produced by energetic events. But anyway, the idea here was to see if you can detect neutrinos and figure out where they're coming from in space. Make a long story short, running out of time, they detected one. I did say one. This one stupid neutrino's got a number, a name. Maybe you can buy adoption papers or something. I have no idea. What they were able to do, though, is get some directionality on it when it came in, back up to the sky. Okay, optical astronomers, search around there, tell us anything's goofy going on. Sure enough, there was a galaxy that had a massive black hole, and there was an outburst. I mean, matched up perfectly. So, here's the press release picture. I want to do that. Yeah, so we all laugh at this because we know how. Obviously, we cheat on scale all the time. We have to. No, come on, this is highway robbery. I mean, the average person looks at that as going to conclude that aliens attack. And sure enough, there's the mothership right here, and it's down there evaporating the South Pole. And that's why the oceans are rising. Anyway, we got to be careful with our illustrations. Otherwise, fine piece of science. But, oh my goodness. You may have heard we've tested general relativity. Of all things using a black hole, of all things using the black hole that belongs to us, the one in the center of our galaxy. The key to this was the European VLT, a very large telescope. It's actually 4 8-meter telescopes, and they are combined through these underground pipelines, and they actually combine their light. It's an interferometer. They can go much better resolution. And they can work in the infrared. They have infrared cameras, which is critical. If you want to look toward the center of our galaxy, you've got to go along wavelengths. Visible light doesn't come through. Too much interstellar does. So you've got to use infrared or radio or whatever. Also, these are still on the ground. They're still looking through the atmosphere. Even the atmosphere above Chile is turbulent. So you have to use adaptive optics. I think this will run automatically. You can watch this change, that piece of sky changing. That turned on and off. This is the case that you shoot the laser beam up in the sky and they get a falling star, they monitor it, and they can then correct the image below. Isn't that amazing? So now what you do, you take this, you have your infrared camera, taking pictures like this, you look and see all the way to the galactic center, and then you take pictures for 26 years. I'm not joking, that's what's been done.
UCLA group you're talking about?
No, this is mostly the European. UCLA does it too, but they've been surpassed, I think, by the group in Europe. European Southern Group. Well, you may have seen this already. Let's see if it plays the way it's supposed to. You never know. Let's see. Well, actually, let me use the mouse. And it always takes a while to start. This is actually a trip into the center of the galaxy, and the European Southern Observatory provided this in full dome, by the way. And that actually works. This isn't going. Yeah, maybe. It drives me crazy. I tested it before you came in. Let's go ahead. I don't have time. So, don't ask me why it's going. Oh, it's also got some hokey space music you might hear. Now, this is mostly just enlarging the view. They get to a certain point, though, they have to switch to infrared because there's no visible picture left. Photons didn't get through. It's about at this point, a little later, we switch over to infrared. Remember, we've got to go 26,000 light years. So be patient. Notice those stars are blue. Come back to that in a minute. Here's the actual data. This is 26 years of those stars moving around. Keep an eye on this guy right here. They're all going around a point about there. That star is called S2. This last summer, it made its closest approach. It got within 17 light hours of the black hole. Only about 3 million miles an hour. We back out again. Notice those blue stars. Blue stars are young stars, recently formed because they're so massive and luminous. Why are they there? In other words, they formed recently. From what and why? In fact, wouldn't the black hole's gravity disrupt star formation? all those orbits now are known. We actually know how things are moving at the center of the galaxy. Let's see if I can get to this. This is that trip around last July. And the thing we were watching was, general relativity says you get into a strong gravitational field. We have gravitational redshift. Speed redshift, you probably all know. The other thing about them is gravitational redshift. Photons trying to leave a strong gravitational field are reddened. It's easy to calculate. The artist here tried to indicate it by changing the color of that star. But that could be measured quite accurately. It did exactly what it was supposed to. Exactly. Given that you have an object in here that's 4 million solar masses. The object you saw nothing of in those illustrations. This star, as it went around, by the way, was going 3% the speed of light. How do you get a giant star going? Well, it takes a lot of gravity. Well, in the universe, there was nothing to make alcohol. All we have is hydrogen and helium. Very boring. The universe, we're now really, again, years back, not that many years back, we always thought we could learn things about the universe history by looking deeper and deeper in space, because you're going further and further back in time. So obviously, as we go deeper, things all look different. And I remember just even when I was in grad school, this frustration that the pictures kept looking the same. Galaxies look, well, they're getting smaller and dimmer and fuzzy, but they look like the same thing. We didn't see any differences. It's only in more recent years, bigger telescopes, you can see a difference. This particular image here is the deepest spectroscopic survey ever done. This is a section of the Hubble Deep Field. And the European Space Observatory used their very large telescope. They have a spectrograph called MUSE. It's another long story, but it's an amazing machine. It can give you a spectrum of every pixel. Down to the pixel level. You want a spectrum? You get one. It's amazing. What they measured was the spectra of 1,600 galaxies. They discovered 72 new ones that Hubble didn't detect. There we go. Blue dot galaxies, this is again early universe. Elmer Green's discovered there's a unique kind of galaxy in the Hubble data set. They look like blue dots. Not clear what these things are exactly. They're like almost no point sources. They're a few hundred light years across. They're not full galaxies, at least not by our standards. The gas content outweighs the matter content, or the galaxy, the star content by a factor of 5. It almost looks more like they're forming globular clusters. Then we got this guy. These things are spinning. We didn't think, if we look further back in time, you're going to find organization to things so early. Because it should be very chaotic. Stuff's falling. In other words, you've got a big bang, you've got a hot universe, a lot of hydrogen helium form. Then it's got to cool enough and be enough, even enough that local spots of gravity are strong enough to hold things together, and stuff's going to collapse at very high speeds, and it's going to be a mess for a while. You're not going to have pretty things forming immediately. You know, I guess we're wrong. These things show, obviously, that they're spinning. They already have the spinning of a spiral galaxy. Then we get to this. Galaxies with no stars. Now, if you have an early universe, not that big bang, and things are cooling down, and cooling down enough that matter can start being pulled together, you might have clumps of mostly hydrogen and helium come together first. Maybe galaxy-sized clumps. But the stars didn't get a chance to form yet. One model predicted that. How would you ever, by the way, we call these dark galaxies? How would I ever see them? Here's how it was done. The center of that picture is a quasar, and those blue circles are marking dark galaxies around it. And they're noticeable. Not in that picture, but they're noticeable because the quasar is causing the gases in those clumps to fluoresce. And so by the fluorescent emission, Lyman alpha in particular, emission line, you can find these big clumps of gas in the universe. You can get the distance from the Doppler. You have a lot of problem with the early universe having really big black holes. They're supposed to take a long time to form because, well, it takes a long time to pull stuff together. Nature didn't pay attention to us. When you detect a quasar, that's a massive black hole in the center of the galaxy. This particular one they're discovered this year has a redshift of 7.5, corresponds to a time 695 million years after the Big Bang. We thought this always took billions of years to happen. But stars didn't waste time either. This is a galaxy. Well, technically, galaxy is light was emitted 550 million light years after the Big Bang. But the point is this: the spectrum shows oxygen, not just hydrogen and helium. So here we are, 550 million years after the Big Bang. It must already have had stars that went through their life, big ones, exploded, spewing heavy elements like oxygen into interstellar media, making the next generation of stars that we're detecting now. All that was done in 500 million years of the Big Bang. That seems almost insane. How you can get out?
No, go ahead.
Go ahead, okay. I want to end with this. This is, I like this picture because I took it. Not so much I took it, I just remember that night sitting there. This is in the mountains of Chile at Saratololo International Territory, here American Territory. And this is just sitting on a deck. Shell and I had a house that let us have, and we just put some lunches on the deck, and wow. There's the Southern Milky Way. There's the Southern Cross. Excuse me. Yeah. I'm having trouble with this little screen, a bit lost. There's Alpha Centauri right there. Down here you can see the top of a building. I don't know if you can see it, I can't. That light on that house is all starlight. All there was. Oh, that's the Eta Carinae Nebula up here. There's a big star that's going to go supernova soon. Whatever soon means. But people all through human history have looked at scenes like this, asked all those questions we talk about. It sounds like I'm getting corny on you. But think about it. All the cool stuff I was just telling you about was built on things that people had done before to build up some understanding. People who froze their tails off at telescopes. I don't know about that. 13 below at Cape Peak one time. So we can just little by little by little put this together. And then us planetariums, I'm part of that group too, have the honor, the ability to tell people about it. This is cool stuff by people who really worked very hard. It's a cool story. When I can, I like to bring in the story of the individual people. Where I can't. We have a cool thing we do, gang. And you know, after you're dealing with so many groups in the planetarium, I know there are time periods you just want to, yeah, come on, check it out, go home. You never know who you've inspired. Often they never come back to tell you. I got inspired as a kid. No, I never went back into the land, but it was the coolest thing I saw in my life. And sometimes in a planetarium, especially these days, we don't see the night sky anymore. I want to end with that and on a lighter note, some parting thoughts. As you go forward, always try to be open to new things. I mean, what could go wrong? I sometimes personally treat deadlines as if they're optional, in university in particular. Well, they're not always optional. You have to sometimes be a little bit more careful about it. lose sight of your mission. It's sometimes easy to do that. You get sidetracked on something. You were trying to get this done. You get sidetracked on this. And now you're going down this rabbit hole and forgetting about the thing that was actually more important and still is more important. And that can happen a lot of ways, like making road signs. I think most of you saw it, guys. Also, the bridge ahead is out. Well, thank you. This has been a lot of fun.
Let's see if we can have a couple questions, and then Shannon has a couple of announcements. Wait, I'll bring the microphone back. Come to the microphone.
Just a quick question about that star S2 at the middle of our galaxy. Do you have just a best guess? Will it ever go into the black hole? And if so, when?
Next week? No, I don't think so. Eventually, the orbit will decay. That's just the way things ought to work.
Right.
And it's going to be probably a long time scale. I have not seen a number on that. I think most people are a little hesitant to guess because you don't just have the black hole effect. When it goes to this outer orbit, now it's feeling the trunks of all those other stars around it. It's an in-body problem. So they treat that with a lot of caution. It will fall in.
I just wonder that wonderful black hole zoom that you did, and then the motion of the stars inside. Where can we get that?
It's all online.
Where is that?
ESO, European Southern Observatory.
Okay, thank you.
It's fairly new stuff. And there's stuff for full dome, pretty cool.
I like asking you what was your favorite, but this time I'll give a twist. What was your favorite of the things that you didn't discuss?
That's hard, because it's my favorite, you heard about it. You know, better list. Oh my, it was so much.
Or perhaps that had more impact for your work?
Well, about the only, but I talked about it, and that was the fact that binary pair is not going to merge in 2022. I was almost going to sick some students on that project. I'm glad I didn't. The light curve is looking a little weird, so I thought maybe it's going to happen. You know, that's real science. I've got a group of 5 students who joined me this fall with the idea they're going to discover an exoplanet. I tried to, you want to encourage them to not false hope. What they learned was, we have a lot of time on a lot of telescopes, and it does get cloudy a lot. And I think we've only got one night of data. And well, that's going to happen. Even though these are really, really good sites, they still connect only weather. It's just the Earth. But I like cultivating that kind of communities. You do too.
All right, well, thank you very much.